So implicit differentiation is just taking a derivative, but it's asking you to take a derivative by a variable that doesn't match your equation. So if you look at this one here, y equals 5x squared plus 8x minus 4, the variable in here is x. So when you go to take the derivative, which is easy, right, 10x plus 8, the name of this derivative is dy by dx, because x was the variable that we were using. What implicit differentiation is going to ask you to do is to find the value of dy by dt, or anything here that's not x. So the trick is that, and we did this with chain rule, that you can take this fraction and you can write it as dy over anything you like multiplied by whatever the matching thing is over dt. So what we're going to leave there then is I'm going to put a dx here, and I'm going to put a dx there. So if you notice this thing, like the dy dx, we already did that. My elbows are all over the place because I don't know how to write in a mirror. The dy dx we already did, and then you have this thing kicking around, which is fine, and in fact is necessary for the question. So you end up with dy by dt is whatever we did the derivative of over there, 10x plus 8, with this dx dt attached. So net, your derivative of y by t would be the derivative of y by x with dx dt, essentially just tacked on the end. So if you were to try that with a different example, and I try to be less theoretical about it, just pick literally anything, like g equals 4 ln x plus 6x squared. The derivative we know is dg by dx, which would be 4 1 over x plus 12x. So that's fine. If I needed to know dg by dt, well, that's just the derivative here, 4 over x plus 12x. And I need to attach a correction factor. So the correction factor that goes here is the variable that I was given by the variable that I'm trying to use. So I've got a match. I have a match here between this t and this t, and then I have this x kicking around up there. We just try it one more time just to show you how quick this is, and really the point here is don't overthink it. Is if I have q equals 3 sine x plus e to the 4x, and I want to know dq by dt, the first question you ask yourself is t the variable you have here, and it's not. So I'm going to put in a bracket. I'm going to take the derivative of this thing here. The derivative of 3 sine x would be 3 cos x. The derivative of that would be, it's a chain rule, so e to the 4x times 4. And because my variables didn't match, I just stick this silly thing on here, dx dt. So if you clean that up a little bit, and you don't have to, you've got the derivative of the thing which you had you knew how to do like a month ago, and you just stuck this thing on because it didn't, the derivative you were asked to didn't match. So why would you ever have to do that? Okay. I was talking to Ms. Wyland about this, so maybe this will make sense, or maybe it won't. Everybody likes Easter eggs, so I'm going to give you 10 Easter eggs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 of them there. Terrible 10. And then I'm going to have you walk down the sidewalk. So sidewalks look something like this. Etc. And on each of the panels of the sidewalk, I'm going to put 4 more little eggs. So you've done this question in grade 9. It's a little tiresome, actually. So you would take the number of chocolates, so let's see, and you will get 4 for every panel of concrete you walk by, plus the 10 that you had in the first place. So that's easy. And calculus so far, for your derivatives, you've been doing, well, this one would be dc by dp. So we'll just do that, dc dp. And that's just a line. So the derivative is really trivial for that one. The derivative would just be 4. Now, you should already know that from the setup. This thing here says the change in the chocolates per panel. That's what dc by dp means. So the change in chocolates per panel is 4. Well, I mean, it's right there, right? There's 4 eggs on each of those panels. I suppose when it comes down to Easter egg hunts, though, you don't really care how many eggs there are per bookshelf. What you're really interested in is how many eggs you can shove in your face or shove in your basket before everyone else gets them. So that's not the change in eggs per panel. That's the change in eggs over time. So I want to know how the contents of my basket are increasing as the clock ticks by. That's not dc dp, that's dc by dt, right? The change in chocolates by the change in time. So if we think about what we did in the last video there, if I were to take this thing and try to do the implicit differentiation on it, dc dt would be dc dp dp dt, and dc dp we already have an answer for, right? We did it over there. So dc dt would be 4 dp dt. So that's it, and that's the answer. But what does that mean? Well, this thing here, dp dt, that's the change in panels over time. And if we're picking eggs up off of these panels, the way you interpret that is the number of panels you get to every second. And if you think about that, the more panels you get per second, the faster you're going. So the number of eggs in your basket over time depends on how fast you're running down the sidewalk. That should make a lot of sense. So this kind of arcane calculus trick, if you think about it in physics terms or in something just as silly as picking eggs up off the sidewalk, you can see where this term is necessary, because we didn't have any information about time. Right? I didn't tell you anything about how quickly you can pick those eggs up. I just told you how many were on the sidewalk. And then accidentally, the math and the calculus pointed out to you that in order to get this particular rate here, you had to know something about the speed at which you were running down the sidewalk. Right? Like, that's kind of neat if the calculus is telling you that stuff, and hopefully it makes some sense to you. Another awkward video down. I'm going to go to bed. Okay, so I changed my mind. We're going to do one more. And hopefully you'll be able to go back and watch the other two parts and think about how I did them in each of the three segments. And by watching all three together and letting that kind of roll around your brain, this will make some more sense. I'm going to stick to the chocolate eggs on the concrete panels just because I thought it was clever, so I'm going to stick with it. So this time, though, the Easter Bunny, or whatever leaves chocolate in your house while you're sleeping, has done something crazy and has followed the following ridiculous pattern for how they leave eggs on the concrete panels. So this one, it looks like you start with your 4 eggs, and then in the first panel there'll be 1 squared plus 2 times 1, which is 2 more, and then in this panel there'd be 2 squared is 4, plus 2 times 2 is 4 more, and then in this panel you'd have 3 squared, which would be 9, which is already getting to be more eggs than I want to draw, plus 2 times 3, which is another 6, etc. So as you can see, the number of eggs per panel is growing quite quickly. So as you go this way and you're scooping up the eggs, not only will it depend on where you are, but it will depend on how quickly you're going through those panels as well. So I'm expecting that dp/dt term to show up again, because it matters how quickly I'm progressing down the sidewalk. But it also depends on where in the sidewalk I'm looking, because the further into the sidewalk, like you can imagine, the panel that's right here has, I don't know, 100 eggs on it, or 500 eggs, or 1,000 eggs. It's quite many. And then the one over here is even larger than that. So when I'm done this, I should see in my change in chocolate over time, I should see something about where I am, so which panel, P, and I should see that dp/dt term, which is how quickly I'm traversing down the sidewalk. So if I'm trying to do dc/dt, dc/dt is, by chain rule, dc by dp times dp by dt. So this is the derivative, just like we've always been doing. So I'm just going to pop that in a bracket. And then this is the correction term, because I was trying to take the derivative of a function with p as the variable by t. And p is not t, so I need the correction factor at the back. And that's really all that is. So to finish this off then, the change in chocolate over time would be dc/dp. So I'm going to look at this thing here, and I need to take its derivative. So the derivative of a p squared is a 2p. The derivative of 2p would be plus 2, and the derivative of 4 is just gone. So I end up with 2p plus 2 dp/dt. So the change in my chocolate over time, it depends on which panel I'm at. If I'm at the 10th panel, this is 22, plus how quickly I'm running down the sidewalk. If I'm at the 100th panel, then I have 202 multiplied by my speed. So you can see how this is getting quite large, and it gets bigger the deeper down the sidewalk I go. This little setup is going to lead you into the first sort of classic differential calculus problem, the related rates problem, where you have something that's changing, but it's mathematically related to something else. So, for example, the volume of a balloon and its radius, right? They're connected. I'm going to erase this. I hope you're okay with that problem while I randomly segue into another one. Let me get rid of this. So back to the balloon. If you were to get on your handy interwebs there and make sure you remember the volume of a sphere, and then I will hope that I also remember it. The volume is 4/3 pi r cubed. And that's for a very specific reason, which if you bravely make it all the way to the integration section, you might be able to piece together. So what we've got there is that the volume of a sphere depends on its radius, and that's all it depends on. The rest of this junk is just constants. So if you think about filling a balloon, right, every time you blow air into that balloon, you are increasing its volume by 1 liter or 2 liters, whatever your lungs can handle. And if you think about blowing up a balloon, you can't increase the volume that's contained in it without increasing the radius of the balloon. Obviously, you can't fill it without it getting bigger. So there has to be some sort of mathematical relationship between how the volume is changing and how the radius is changing. So if I were to do dV by dr, that would be really easy. But I'm talking about filling a balloon over time. Maybe you're adding 1 liter per second. Maybe you're adding 40 liters per second. We're going to put a number here in a minute. But in order to do dV dt, when r is my variable, I have to do this implicit differentiation thing. So if I set that up, I have dV by dr, which is the derivative I can do, multiplied by the correction factor, dr by dt, because r is the only letter in my equation, and t is the only letter that I was asked to do the derivative by. So dV dr, the derivative of an r cubed, you bring the 3 down, so I'd have 4/3 pi times 3r squared, and then I have this silly thing kicking around. So 3 times 4/3, these just divide each other out. So I'm left with the change in volume over time is 4 pi r squared. Forgive my handwriting. That's an r, and so too is this. So you have dV dt being 4 pi r squared times dr dt. So if you can do that, and then we can ask each other a whole bunch of questions, like if I were dumping 5 liters per second into this balloon, you put a 5 here, and then ask you how is the radius increasing? Well, you notice that this r is still there. You have to fill in the specific value. Just like the eggs on the sidewalk, the further down the sidewalk you went, the more eggs you were getting per panel. Well, that's the same here. The bigger the balloon gets, the more air you have to dump in order to stretch the latex further. And we're going to do more about that. We'll be more specific about that later. But I just wanted to toss that in there to give you an idea of where this was going. The last thing I want to do is one with 2 variables. So we're going to have to use some product rule to do this. So quick, what's an easy volume formula that has 2 dimensions multiplying each other? Oh, excellent idea, the cylinder. So the volume of that is pi r squared h. So if I'm going to let the volume increase over time, so I want to let it either grow or shrink, it doesn't matter, dV dt. In order to get dV dt, I have to take the derivative of this thing. Now, pi is just a constant. So pi is just kicking around. But I have a thing times a thing. So I'm going to have to use product rule in order to do that. So I'm going to set up my little boxes for product rule. Hopefully I have enough room without my fat head getting in the way. Okay. So the derivative of pi r squared would be 2 pi r. But r is not t. So in order to take the derivative of that r, I need the correction factor. So I'm just going to park her in there. And then h gets left alone. Second block here, I leave the pi r squared alone. And then I have to take the derivative of h. Well, the derivative of h would just be 1, but h is not t. So I need the correction factor in there again. So let me write it in for you. Okay, now it's a big, long, ugly thing. Do you notice that there is a pi here and there's a pi there? So I'm going to factor it out. There's also an r here and an extra, there's 2 powers of r there, so I'm going to pull one of those out. And that leaves me with 2h dr dt and r dh dt. Okay, now it's interesting that you have 2 of these things, right? There's a change there and there's a change there. So if I were to just really hope I can draw you a cheap cylinder here. There. If I want that thing to grow, there's 2 ways I can do it. I can let it grow this way. So that would be letting the height change over time, right? It would be getting taller or shorter. Or I can take the radius and let the thing dilate this way. That would be allowing the radius to change over time. And better? Can't even see that. My inner perfectionist won't let me leave that there. dr dt. Now, you didn't think about this when we started, because who thinks about these things? But if you start with this volume formula, right, pi r squared h, which you've been using again since grade 9, and you want to take something as simple as a can and let its volume change, this arcane trick, right, just implicit differentiation, when applied to that type of formula, has pointed out that you can grow a can in 2 different ways. You can either let its height change, or you can let its radius change, or you can do both. In fact, and this is where this gets interesting from an engineering application point of view or from a physics point of view, it's possible that you can let the height change, let the height grow, and let the radius shrink so that these 2 things match each other. And if you could come up with a way to do that, you would have a can that maintained its volume. So you're not destroying or creating material. You've satisfied conservation of matter, but it's able to grow and shrink, right? So it's able to squish itself. And if that's a key component to whatever mystery machine it is that you're building in your lab, then if you can figure out how to code those 2 equations so that they balance each other, then you've created a system that sort of rocks back and forth. Now I'm rambling. The point here was, can you take the derivative of this thing, which has an r in it and an h in it, can you take its derivative by t? Well, you can. It's just every time that you go to take the derivative of something that's not t, you have to put in that dh dt correction or the dr dt correction. so that you have all the right parts. It is getting late and I am getting rambly, so I'm really going to stop this time. I hope that made some sense. And I think when you get to the related rates questions, where we actually start doing this about something, it will maybe make a little more sense what you're up to. But I really want to underscore the point that implicit differentiation is just taking a derivative like you've always been doing, and then tacking on that correction factor at the back. So if you can keep that in mind, then the problem sets are maybe not quite as scary as they looked in the first place. Okay, good luck.